I've crossed all this out because there's an idea behind it, but it doesn't pan out and it's not necessary. So we're going to come down here and say this. If f is a function of x and y, so you have an f of x, y. I'm going to have to make a couple notes over here. So you got f of x, y, where x is a function of t and y is a function of t. Then the derivative of f with respect to t, I say, is the partial with respect to x, partial of f with respect to x times the derivative of x with respect to t, plus the partial of f with respect to y times the derivative of y with respect to t. Okay, now why would this be true intuitively? Well, this is how much f changes with respect to x. It's the rate of change of f as you move in the x direction. But x is a function of t, so a change in t causes x to change at some rate, and that rate is dx dt. So if x is being driven to change at this rate, and a change in x changes f at this rate, you multiply those two rates, and you get the rate of change of f with respect to t for motion along the x direction. Okay? And you get the same thing for y. Okay? This is the rate at which y drives a change in f, and this is the rate at which t drives the change in y. Okay, so if you multiply these, you get the rate of change of f as you move in the y direction at speed y of t, essentially. Okay? Now that's very much related to what we've said about tangent plane rates of change. And remember how we got the two vectors tangent to the graph of f of x, y versus x at a given point. Okay? And we got the tangent vector here and the tangent vector here, and we took the cross product, we got the normal vector, we got the normal plane, and the normal plane models the change in the function f near the point of tangency in terms of the rate at which the function changes in the x direction and the rate at which it changes in the y direction, and you just add those two, the two resulting changes. Now here we're just saying, okay, x is changing at a certain rate in time, and y is changing at a certain rate in time. So whatever rate f changes with respect to x, you multiply that by the rate at which x itself is changing with respect to time. How fast is x changing? And same thing here. So for example now, and I crossed out a bunch of stuff up here that I now want to use. What I crossed out up here is if x of t equals sine t and y of t equals cosine t, and you have this function that I specified here, f of xy equals 2xy plus 3x squared y cubed. So somehow I've got to delineate all that. Okay, so we've got this. It's not crossed out anymore. It's 2xy. I'm probably making it harder to read, but 3x squared y cubed. And x is your sine function, and y is your cosine function of t. Okay, so, well, I'll repeat the f of xy here. Same thing we had up here. And if x is the sine of t and y is the cosine of t, then substituting the sine and cosine, I get this. So that df dt is this. Now, you know, the algebra is very simple. Well, actually the calculus, I mean, the derivative of the sine is the cosine. So applying the product rule here, we're going to get a cosine squared. And then applying the product rule, taking the derivative of the cosine times the sine, we get a sine squared. But it's negative because the derivative of cosine is the negative of the sine. So all this follows very simply from the derivatives of your trig functions and the product rule. So you can work this out and verify that all this is correct. It's very easy to work out. You can probably work it out more accurately than I'm likely to. Okay. Now, that's what we get if we take this function and plug in these x and y functions for the x and y. Okay. Now, over here, we do it using the chain rule. Okay, because there are some serious advantages to using the chain rule. Not so much for this problem, although it's maybe a little easier. So, we say what? Our df dt, according to this chain rule, is partial x with respect to x, which I write as fx for brevity, times dx dt. What's dx dt? Well, if x is the sine, dx dt is the cosine. So right here, we've got our fx and our dx dt. Fx times the derivative of this x function with respect to time. Derivative of the sine is the cosine. And then our fy here times our dy dt. Well, y is the cosine, so dy dt is the negative of the sine. So we get negative fy times the sine of t. And I've got a little note up here. The cosine is your dx dt. The negative sign is your dy dt. Now, I didn't include the negative in what I identified as the dy dt, but that's where the negative came from. Okay, so if you just apply this without trying to figure out what I did, you will see that what you get matches what I got. Very straightforward, very simple substitution. Okay. Then our partial f with respect to x is easily calculated. If this is our x function, then we're going to get a 2y here, there it is, and we're going to get 6xy cubed here, and there it is. And that's going to be multiplied by cosine of t. And then our fy is, is 2x, there's our 2x, and 4 times 3, which is 12, but, wait a minute, or fy, not 4. Fy is 3y squared, right? So we're going to get 9x squared y squared, and there it is. And that's going to be multiplied by our sine of t. And it's actually our, fy is a negative sine of t, but the negative is here and the sine of t is here. Then we plug in cosine t for y, sine t for x, and simplify this, and we find that it's exactly the same as this. They have plenty of exercises that are assigned that ask you to do that sort of thing. And it works out. Okay, I've got a little note down here about the differential. And try to figure out why I did that, mention it in the next clip.